this video, we're going to define what it means for a set of vectors to be linearly independent, and we'll talk more conceptually about what that means exactly. Okay, so I'll begin with the definition. So let's let v1, v2, all the way up until vk be elements of Rn. So they're vectors that each have n entries. So we say that the set of vectors is linearly independent if, when we form a linear combination of those vectors that equals 0, the only way for that to be true, the only solution this equation has, is the trivial one, where c1, c2, all the way up until ck equals 0. Because we've seen before that when we look at a homogeneous system like this, the trivial solution always works, but if that's the only solution, then we say the vectors are linearly independent. So I'm also going to word this in another way. Because when I form a linear combination of these vectors, I can also write this in matrix form. It's the same thing as forming a matrix that has v1 up until vk as the columns, multiplied by a vector where the weights are c1 up until ck. And then this equals the 0 vector. So what we're saying is the vectors are linearly independent if this matrix, which I'll just call A, times this vector, which I'll call X, if the only solution is the 0 vector, the trivial solution. If this only has the solution where the vector X equals 0. So I'd encourage you guys to think about, well, when does that happen? If you have something like A times X equals 0, we know that this always has a solution, at least one, 0. The 0 vector always works. So if a system like that is consistent, when would it only have one solution? So maybe what's coming to mind is this idea of free variables or not. It turns out this is going to be true. The only solution is going to be the 0 vector if and only if the vector, none of the columns have free variables. Because if there were free variables, we'd actually have an infinite number of solutions. And I'll state that a bit later. Okay. On the other hand, if there is a solution, so if there's something I can plug in for C1 up until CK, where not all of the CI's equal 0, then we say that our vectors, V1 up until VK, that set is linearly dependent. Okay, so let's look at an example. So here's the example. So notice that if you take 4 times the vector 5, 3, 1, minus 10 times the vector 2, 1, 3, plus 2 times the vector 0, negative 1, 13, if you just check this computation, we end up getting 0, 0, 0. So because there is a linear combination of these 3 vectors that equals 0, and it's not just the trivial one, where each of these weights is 0, what does that mean? Does it mean the vectors are independent or dependent? Pause the video for about 20 seconds and think about that. Dependent or independent? This means that they are linearly dependent. Because there is a solution where not all of the CI's equal 0. Okay. So intuitively, what does it mean for vectors to be independent on the other hand? So intuitively, a set of vectors v1, comma, dot, 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 up until vk is linearly independent if and only if v1, v2, comma, dot, 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 up until the last vector in the set, vk, are in, and I'm going to put this in quotes because it's kind of informal, if there are completely independent directions. Okay. So of course now that begs the question, what does that mean? What does it mean for these vectors to be completely independent in completely independent directions? So the easiest way for me to answer that is to do an example. Okay, so I have these 2 sets of vectors. So this one in blue, which has the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. As we'll see, in this chapter and a little bit more in subsequent chapters, these particular vectors where I have 1, 0, 0. Like there's one entry that's 1 and everything else is a 0. These show up a lot in linear algebra. Okay, so that's the blue set. And then I have this green set where the last vector is different. It's just changed to 1, 1, 0. So I want to answer, are these vectors linearly independent or dependent? So it turns out this first set is linearly independent. They are in completely independent directions. So what do I mean by that? If I were to draw a picture, so this is in R3, in 3D space. So I got my x-axis, got my y-axis, got my z-axis. So if I draw the first vector, 1, 0, 0, that goes in the x direction, 1 unit, but no steps in the y or z direction. So 1, 0, 0. The second vector is in the y direction. So this is where the vectors 0, 1, 0 is. And then the third vector is in the z direction. That would be this vector, 0, 0, 1. Okay, so conceptually, these three vectors are in what I'm calling completely independent directions. And I think that will be a little bit more clear once I compare it to this next set, so the one in green. This one happens to be linearly dependent. So let's draw these and talk about why conceptually these ones are dependent, why they are not in just all independent directions. So I got my x-axis, my y-axis, and my z-axis. So the first vector is the same as before. It is 1, 0, 0. The second vector is in the y direction. That's the same as before. That is 0, 1, 0. But the third vector doesn't go outside of the xy plane because the z component is 0. In fact, if I draw in that third vector, it goes 1 in the x direction, 1 in the y direction. That's something like this. In fact, if I were to sort of go 1 unit in the x direction, 1 unit in the y direction, this red vector is actually what I get if I sort of take this first vector, take this second vector, and add them together. That's the vector 1, 1, 0. Conceptually, this red vector is not in a completely independent direction from the first two vectors, because this is in the span of the other vectors. So it turns out if one of the vectors in my set, if at least one of the vectors in my set is in the span of the other vectors, if I can write it as a linear combination of the others, then the set is linearly dependent. But I couldn't do that with these blue vectors. None of these three vectors is a linear combination of the other two. Okay, so now let me just write that result down. Okay, so this is actually a theorem which says that a set of vectors v1 up until vk is linearly dependent if and only if at least one of the vi's, one of the v vectors, is a linear combination of the other vectors. And that's sort of conceptually what we just realized in the picture that we drew before this. One thing I really want to point out carefully is that it is not necessarily true that every vector vi in the set is a linear combination of the other vectors. Because this statement just says at least one vi is a linear combination of the others, but it doesn't specify which one has to be the linear combination of the others. So be really careful about that.